Sure, okay.
Okay, good evening. Am I audible?
Yeah, good evening.
Yes. So welcome to this week's tutorial session on this course Computational Fluid Dynamics offered in NPTEL by Professor Srinivas Jayanti and Sankar H. I'll be your teaching assistant for today. In this lecture, we'll go through some of the graded and ungraded assignments of previous week, that is week number 10, which deals with multiple iterative methods and convergence criteria of various schemes. And with that, let's get started with the previous week's graded assignments. So, in the first question, before we start the first question, they have given us a paragraph for us to read, and that is we are solving a Poisson equation in two-dimensional form as shown in this figure. And the rectangular domain EFGH is has a constant source per unit area, and side AD is a Neumann condition, which refers to an insulated or a derivative at the point is specified, at the AD is specified. Now, AB, BC, and CD are actually Dirichlet conditions where the function value at the boundary is mentioned or is specified. Now we use in uniform mesh and use a second order accurate discretization of the Poisson equation. And you wish to have you wish to solve the resulting set of linear algebraic equations which you have expressed in the matrix form as Px equal to Q. And for this problem, we have to answer the following questions. So let's take a 1 second. Excuse me.
Just a general question. How
Sure.
is it that so few people join the call? Or is it because it's a weekday?
I'm not sure exactly. I guess on the
Okay.
weekend as well. On the for the previous tutor as well has very as few as 1 or 2 students as only.
Wow. Because
I
I
guess
think
most
more than
students don't.
1,000. Yeah.
Yeah, I guess most students don't find these sessions very helpful, or maybe they've just registered, have not enrolled for the courses. Either or could
Ah,
be.
okay.
All right, so let's start by defining what this question is. What they have given us, let's assume that we are talking about temperature profile over here around this slab. So we'll write the Poisson equation as del square T is equal to some source term. So we can write alpha del square T is equal to some source term, and I can rewrite this in the two-dimensional form or two-dimensional domain as dou square t by dou x square plus dou square t by dou y square is equal to s some constant s, let it be the source term or the that's given here, and therefore I can discretize this by a second order accurate central difference scheme as Ti plus 1j minus 2Tij plus Ti minus 1j divided by delta x square plus Tij plus 1 minus 2Tij plus Tij minus 1 by delta y square should be equal to Sij. And then we rewrite this. Write all the equations after discretizing this in n number of rows and n number of columns, and rewrite this in a matrix form p times, let's say the x vector here is a temperature is equal to a q vector, or let me put it in the notation that's given, q vector that is on the right side. Now we know that the side AB, BC and CD have temperature at those locations specified to be some T1, T2 and T3, and at side AD is the derivative of the function is present, let's say dt by dy at AD is given out to be some constant, let's say C4. Now we have to answer the following questions based on whatever we have learned till now. In which of the first question is, which of the following can be used to solve Px equal to Q from the above problem? The ADI method, the incomplete LU decomposition method, or the tridiagonal matrix algorithm? Would you like to
One and
answer?
two. One and
Yeah.
two.
The ADI method and the ILU method can be directly used to solve, as we have seen in most of the lectures that Professor Srinivasan has mentioned. But the tridiagonal matrix involves the or necessitates that only one-dimensional problem or tridiagonal matrices can only be solved here. So therefore, the tridiagonal matrix algorithm cannot be used to solve such a equation Px equal to Q.
While on this TDMA, could you get an answer for my question as to why TDMA requires diagonal dominant?
So I checked with Professor Srinivas Jayanti. Apparently, I didn't get any reply from him directly, but I searched all over, and it's just that the TDMA actually does not require, or is not. Let me phrase it right this way: is not an iterative method,
Right.
so it does not require diagonal dominance.
Mm.
So that answer to the previous week's lecture was actually wrong. I think
Okay.
only that statement what you have said for the previous week is actually correct.
Mm.
So therefore, no diagonal dominance condition is required here, as far as I know.
Okay.
And I've checked everywhere through some of the literature, some of the textbooks, and through the internet, and I also found this answer to be satisfactory enough for me to proceed. So the maybe the previous week's assignment could have had a wrong option over there.
Yeah. Okay.
Now, which of the following methods cannot be used to solve Px equal to Q for the above problem? Is it the successive over relaxation method, the multi-grid method, or the strongly implicit procedure method?
All can be used.
Yeah, so the correct option, or is it the secret option number 4, is all can be used. I think this was a multiple choice question, and the option given here is the all can be used over here, and none of these not cannot be used, or the double negatives comes over here. So all of these methods are satisfactorily used to converge and can be solved such an equation arising from the discretization of, or the solution, or finding the solution of uh, a system of linear equations that arises and can be written in the form Px equal to Q. Yeah. So therefore, all these methods can be used. moving on to question number 3. Which of the following statements is true about the source term in the region EFGH? So the source term comes over here in this small region of it. First one, it strengthens the diagonal dominance of the discretized equation in the region. Second one, it weakens the diagonal dominance of the discretized equation in the region. Third one, it affects the column vector Q.
Only Q.
Yeah, that is correct. So when we had written down the equation in this manner, we see that the source term comes only over here and does not affect the coefficients of the unknown variables ti, j, I plus 1 j, I minus 1 j, and all such terms. So the diagonal dominance of the discretized equation does not is unaffected by the source term. It only affects the column vector q, and that is the correct answer. The first and second statements are in fact wrong.
That's only the coefficient matrix, the diagonal dominance and all that.
Yes, only the yeah. Sorry, yeah, only the. I'm
Coefficient
sorry.
matrix, yeah. Yeah,
Yeah, coefficient does not change when the source term is present.
correct,
Only the,
correct.
yeah, that's also that's correct. Okay, moving on to question number 4. Which of the following is true about the side EH, and that is this side on the domain where the source term is present? Option A, Dirichlet boundary condition is applicable on EH. Neumann boundary condition is applicable on EH. Option C is Robin boundary condition is applicable in EH. And option D is no boundary condition is applicable on EH. So let me just mention what this is. The Dirichlet boundary condition refers to the function value at the boundary EH is some constant C1. Neumann boundary condition refers to dt by dy, or the derivative of the function at the boundary EH is given. Robin condition refers to a combination of Neumann and Dirichlet, whereby uh, it some the boundary condition can be written as some linear function of, or a linear summation of the derivative and the function value at the same point. And option D is none of these are true.
That question it confused me because I mean obviously no boundary condition is applicable
Yeah,
on that,
yeah,
but I thought it was a question because EH, like the your corner H
yeah.
would be influenced by CD, right?
By AD, right? Is
No,
that what you're
CD,
saying?
CD.
CD.
I'm just looking at it. It looks like it's one grid point away.
Huh. Yes,
So
the temperature over these points would definitely be affected by that. Or let's say the function value at the, let's assume the temperature is the point in discussion. So the temperature at each of these points on the on this EH would definitely be affected by these boundary
yeah,
points over here, and the uh, what this insulation over here, or the Neumann boundary condition at EH. But we can't directly say that any of these boundary condition is directly applicable on the domain or on the source term. This is actually an interior point if you think about it. Suppose the source term was not there, then definitely we can't apply a boundary condition over here. Similarly, just because a source term is there, we can't put any of, or we can't translate any of those boundary conditions at the at the four boundaries onto this domain source term. Yeah. I hope that answer. I think this question was again raised inside the forum as
yeah.
well. Am I right?
I thought it was a sort of a question which I mean because the no BC is obviously not applicable. I mean is applicable just looking at it.
Yes.
So I thought maybe the question was sort of more involved.
No, actually, it's very pretty straightforward. There
Pretty
was nothing
straightforward,
to.
yeah. I
Yes,
mean,
yes.
you could put pretty much any region inside this box, and they would
Yeah,
all have no
exactly.
bound. Yeah.
Yeah, none of these would, any interior point, none of the interior points would correspond to a boundary condition at all.
The way I looked at it was H point H is one grid point away, one delta x away from site CD. So
No, we
the
have
way
not mentioned anything
I know,
about the way
I
in which
know.
it was discretized. Yeah,
So that's the way I looked at it. Yeah.
I see. Okay. I hope this answers that question then.
Yeah, yeah. I mean, it's a pretty straightforward question. Yeah.
Yes. Okay, moving on to question number 5. Which of the following statements is true about the successive over relaxation method if the coefficient matrix is diagonally dominant? So it is stated that the coefficient matrix is diagonally dominant, therefore we do get a converging. Oh, sorry. We can't say anything about the convergence right now since this is a successive over relaxation method. So the first statement is its convergence rate increases monotonically with the parameter omega. This is not W, this is actually omega. And second statement is it is convergent if omega 0 less than omega less than 2. And third point is its convergence rate is twice as much as that of Gauss-Seidel method. Which of the statement would be true?
It is two.
Yeah, only the second statement is true,
Yeah.
as because if omega is its convergence rate does not monotonically increases with the successive over relaxation parameter, there is an optimum parameter that can be found out that is given in the lectures before and after which the convergence increases. So before and after which this convergence increases. So at the optimum omega, that can be anywhere between 0 and 2, it is found to be the maximum rate of convergence, after which convergence rate generally increases. And the second statement is it is convergent if 0 less than omega less than 2, and that again has been is the condition for successive over relaxation method. There is a lot of mathematics behind this. I am pretty sure that was not fully covered in the lectures as well, because that has more mathematics behind it than the CFT technique behind it.
Yeah.
And the third point is its convergence rate is twice as that of Gauss-Seidel method.
There's a
So
formula there. Yeah.
Gauss-Seidel method, and so the only difference between successive overlay selection method and Gauss-Seidel method is the iteration value has some parameter omega times the difference in the the difference in between them, whereas for the Gauss-Seidel method, where we use directly the values of whatever that has already been uh, done, that whatever has been evaluated at j less than I. Suppose I am evaluating at I, then be j less than I plus the values at j greater than I over here. So we evaluate the Gauss-Seidel using this way, and we evaluate the successive or relaxation using this way. Therefore, we can't generally say anything about the convergence rate as it is, but we know that the Gauss-Seidel method has is the number of floating operation points procedure. The flops is proportional to n square, whereas for successive over relaxation it is proportional to n raised to 1.5. So it's not necessarily twice as Gauss-Seidel method. So only the second statement is correct. Right. In comparison with the Gauss-Seidel method, the number of floating points operations required from one iterative step of going from xk to xk plus 1 uh, using the successive over relaxation method. Oh, yeah. In comparison with the Gauss-Seidel method, the number of floating points required one iterative step of going from xk to xk plus 1 using the successive over relaxation method is would be the answer is here.
C.
Yeah, it would be roughly about the same. And we just saw that the optimal SOR has a relation of n raised to 1.5, and the Gauss-Seidel has an n square n square relation. So it would be about the same over here. Okay, question number 7. The alternating direction implicit method for the solution of Ax equal to B is based on the decomposition of matrix A into m plus n, the problem into two dry diagonal matrices, matrix A approximately into L and U, and none of the above.
That is B. To
Yeah,
try
the
diagonal.
yeah, technically this
2D.
statement should,
Yeah, yeah.
yeah, this statement is only option 2 is actually only true for the
2D.
two-dimensional problem
Yeah.
as raised by a student in the forum, and I had answered personally to him. I think I have not answered it publicly
Okay.
because this statement is what the argument was is that it's only true for 2D. Therefore, the correct answer would be none of the above. We generally do not deal with, or the question is not phrased on whether it is dealing with a two-dimensional
Correct.
or three-dimensional problem. So it's the second statement is only true for two-dimensional case. The correct
Correct.
answer is D then. Right. Question number 8. In the strongly implicit procedure method for the solution of Ax equal to B, the matrix A is decomposed into which of this following? Yeah, the in the strongly implicit proof method, the matrix A is actually decomposed as Lu plus N, where we have uh, with this the explanation for this is directly from the lectures. So I think we just need to it is directly given from the lecture and has nothing to be thought about. And I think
Yeah,
they'll yeah,
it's a sort of a degraded version of an
ILU.
LU,
Yeah,
perfect
ILU
LU.
method. Yes,
Yeah,
exactly.
yeah,
So,
yeah,
and it's pretty straightforward as well. So, I'm
yeah.
not going to further discuss it anymore with this.
Yeah.
So, moving on to question number 9. Which of the following statement is true about the multigrid method of solving Ax equal to B? First one, it uses several grids for the same computational domain. Second one, it solves the same equations on all the grids. Third one, it uses the same boundary condition on all the grids.
First one is correct. All the
Yes, it
same equation, correct.
yeah.
Same
So
boundary. Yeah, I guess all three.
not exactly. It uses the several grids for the same computational. It uses several grids for the same computational domain. So that statement makes sense when. Let me put that. Let me just describe what the question is asking. So let's assume that we have a domain like this, which is finely discretized like um, 1, 2, 3, 4, 5, 6. 1, 2, 3. Oh, excuse me. 3, 4, and it is basically coarsely discretized as 1, 2. Let's say 1, 2, and 3 somewhere here and here like this. So we see that these two grids together, we use the first finer grid for the solution of, for to eliminate the shorter wavelength errors, and the coarser grid to eliminate the long wavelength errors. So we use several grids for the same computational domain, but we are not exactly solving the same equation on all the grids. Although we are dealing with the solution of, let's say, dou square t by dou x square plus dou square t by dou y square is equal to some Sij or source term. We discretize this in two different manners when we find the answer for the fine grid and the coarse grid. Let's assume that the I or I is small over here, then I would be, let's say, capital over here. We see that these two are differentiated in two different manners where Ti, let's I plus 1j minus 2 Tij plus T I minus 1 j by delta x square plus something by delta y square is equal to Sij, whereas here we use t, capital I plus 1 j minus 2 t, capital I, sorry, I minus or ij plus t, capital I minus 1 j by delta x square plus the same for ij plus 1, this would be capital everywhere by here again delta y square would be capital equal to s capital I capital J. So we see that the we are not in fact using the same equation on all the grids, and the equation refers to the discretized equation over here. We don't discretize in the same way is what is being asked, and that statement is actually in fact false.
Okay.
And option 3, it uses the same boundary condition on all the grids. That statement is actually true, as we do put these elements, although we are solving at a coarser grid or finer grid, we are saying that the boundary condition effectively remains the same. As let's assume that this is, I think, A, B, C, D given like this. In both the coarse grid and the fine grid, we are saying that A, B, B, C, and C, D have the Dirichlet condition, and the boundary AD has a Neumann condition as given in the problem that was stated in the first page. So option C is correct. No, option 3 is correct here.
Yeah. Okay.
Alright, moving on to question number 10. The multigrid method is efficient in solving Ax equal to B because first point is only part of the computations are solved on the grid. Second one is computations on coarser grid takes lesser computation time. And third one, computation on coarser grid takes fewer iterations to converge.
All three.
Yeah, all three would be correct because we know that, let's go through these 2 points first, because we know that a coarser grid would require fewer number of nodes or fewer number of points, and therefore would be would have much lesser computational time, and would take much or fewer iterations to converge. And when we solve the equations on the fine grid, we are doing some part of the calculation, and then when we move on to the coarse grid, we are doing other part of the calculations. So only part of the computations are solved on the grid as is, especially when we are doing in the coarse grid as well also.
Correct.
Yeah, so therefore all the three statements are correct here.
Though that, like that questionnaire posted, the
Yeah,
first thing should have been solved on the fine grid. Should have been the wording
yeah,
of that.
yeah. I mean, yeah, there is a statement over here, but overall we do say that not all the computations are solved at the same time.
Yeah.
We say that only part of it are solved, then again we change the grid and then solve the rest of it. And therefore, that statement would be correct in my argument. That's it. Although phrasing can be a little bit better here,
Yeah.
or a couple of words may be added to clear any confusion. I agree that. Okay, with that we have completed the graded assignments for week 10, and before we move on to the non-graded assignments, we'll just take a couple of minutes break and come back to this.
Sure.
Okay, we can resume our session to now.
Yeah.
So the first question for the non-graded assignments was, which of the following statements is true about the alternating direction implicit scheme or ADI scheme? It is an iterative method. It requires diagonal dominance to converge, and it can be applied to three-dimensional problems.
Yeah, all three.
Yes, we see that the alternating direction implicit methods what decomposes the problem into, let's say, a 3D problem into three one-dimensional problem and solves them in an iterative manner, and then finds out the solution. And it's just because, and since it is an iterative method, it has the condition of diagonal dominance for convergence, and therefore all the three statements are correct. And yeah, all the statements are correct. Question number 2, which are for the solution of Ax equal to b, which of the following decompositions of matrix A is the most implicit? Is it the LU decomposition, or ILU, the incomplete LU decomposition, or an LU plus N as in the strongly implicit procedure method? I think C
Is
and
it
D are the same.
ILU
No, so when we
or just LU?
decompose the
Yeah.
matrix A into an incomplete LU method as shown in so we write A as, let's assume that we are writing A phi is equal to B, and then we would be decomposing this as LU phi k plus 1 is equal to B minus N phi k. One second, there was someone else who wants to join. Yeah. So LU phi k plus 1 is equal to B minus N phi k, and we solve first, so we solve this and then we solve U phi k plus 1 is equal to Y, uh, where Y is equal to yeah, where, sorry, where this is what we are first solving. Ly is equal to B minus N phi k. So we see that there is an explicit function. This is actually an explicit as when we solve for A over here. Whereas when we do the LU decomposition, and this strongly implicit procedure again is a further follow-up of this. Therefore, that also has some explicit nature of A that is found, that arises from the guess estimate or the estimate of this phi k over here. Whereas the LU decomposition just decom or just breaks down this A phi equal to B as LU phi is equal to B, and we solve for Ly is equal to B and U phi is equal to Y. Therefore, this method of LU decomposition is the most implicit over here, as every calculation is done on the k plus 1 or the same stage, same level.
Yeah.
So the LU decomposition is the most implicit. Question number 3, if n is the number of grid points on the finest grid, then the number of floating point operations or flops required to achieve a given level of convergence in the multigrid method varies as n raised to p, where the value of p is about, that's being asked. And the lectures, yeah,
1.05. Huh?
yeah, 1.05 is the correct answer. The lectures sir had mentioned that for the
Yeah.
multigrid method, it actually varies as n. In the lectures, it was mentioned that it varies as 1.1.
Yeah.
For, let's say, Gauss elimination, it varies as n cube, and for Gauss Seidel, it varies as n square. And for, as we have seen earlier, the optimal successive over relaxation varies as n raised to 1.5, and there are other methods also which vary as n raised to p, or whatever the p values are. And so for this question and the multigrid method, the n value varies as 1.05. the p-value varies as 1.0. Okay, question number 4. Advanced iterative techniques are primarily used to enhance which of the following aspects of basic iterative methods?
Basically, only the convergence first
Yeah,
two.
in all the advanced iterative techniques such as ADI or in multi-grid method or the strongly implicit procedure, we see that it converges faster,
Yeah.
and it has an easier convergence condition, or a relatively easier convergence condition, and we try to converge it faster. Therefore, the first two statements make sense, but it is extremely computationally intensive, and therefore only the first two would uh, is correct. Okay, moving on to question number 5. Which of the following statements is true about the multi-grid method of or for solving Ax equal to b? Option 1, it uses multiple grids for the same domain. Option 2, it uses multiple grids for the same equation. Option 3, it solves the same equation on all the grids.
We just did this, right? Only one and two.
Yeah, we have just seen how only 1 and 2 comes,
Yeah.
and the third one, it doesn't solve the same equation because of the way in which it is discretized. So we
Yeah.
use
Yeah.
multiple grids for the same domain and for the same equation. So I think with this we have come to the end of the non-graded assignments for week 10 as well. I wish to follow up what where we have left behind for the example question, where we have tried to analytically define or analytically derive the equation of fluid flow for a fluid in a rectangular channel, and which is pressure driven flow for a steady incompressibly fully developed laminar flow of a Newtonian fluid. And we are doing this derivation in one of the earlier lectures, and I just finished to complete it. I think I left it at the last step over here.
Yeah.
So let me just recap on what we have done till now. I think we started by defining the Navier-Stokes equation, uh, and we restricted to a one-dimensional problem, and neglect the velocities in the y and z direction, and we assume that the flow is only in the x direction. We assume a steady state incompressible fully developed laminar flow as given in the problem. Therefore all these terms, all the relevant terms have gone to zero, and we find an elliptic equation in u, and we find an elliptic equation in u in terms of y and z, the coordinates y and z, as follows, where mu into dou square u by dou y square plus dou square u by dou z square is equal to dou p by dou x, and the pressure gradient is constant over here. And we started by splitting this actual velocity into a sum of a general plus a particular solution, and we said that this particular solution uh, is once again, yeah, we said that this particular solution is a pressure driven flow between two plates, and this general solution is when we put this walls between them, the error that is caused due to the walls between them can be said as the general solution, and a particular parallel plate solution will be given when this wall, the distance between these walls is tending to infinity. Therefore, we try to find out what the general solution and parallel plate solution is, or a particular solution is, and the general solution was given by d square ug. It becomes a completely in a straight or the normal differential rather than the partial differential, as ug is only a function of y, and we said that d square ug by dy square is equal to 1 by mu dp by dx, and we integrated twice and found the equation for and used the boundary condition, which has the walls, no slip at the walls, and a stress free condition at the center of the domain, and found the expression for the general velocity profile, general solution for the u velocity as h square by 2 mu dp by dx into 1 minus y square by h square. And this is actually the I think I have not mentioned this. I think I'll use a different color over here. So this is actually the Poiseuille equation, or the
or flow
okay, this
between parallel plates.
yeah, Poiseuille equation for pressure-driven flow between two parallel plates. Next, after that, we found out how the boundary condition for the particular solution looks like based on the actual velocity and the general velocity profiles. And we said that the particular solution will, particular velocity will have the boundary conditions, that is the difference between the actual and the general. And since this is because the governing equations are linear, and therefore the boundary conditions also will be linear. And we found the we first found out the governing equation for the particular solution, and we then found out the boundary condition for the particular equation, which is basically the difference between the boundary condition of the actual profile and the difference and the general solution at each of these four points. And the important part to note here is that the general solution for z equal to plus or minus b, when this wall was there, was not there or there, the general solution does have a value, whereas the actual solution shouldn't have a value. Therefore, we argued that the particular solution, the boundary condition of the particular solution, should be the negative of the general solution at that point over here. And the rest of the boundary conditions are basically quite straightforward. And then we used the governing equation along with the boundary condition and tried to solve it using a separation of variable method, where we split the function up as a function of y and z. And we are not, we technically speaking, we won't be sure whether this separation of variable will indeed give us the right answer. So we just have to go for a trial run and check if we are able to get a solution, and then come back to it and find another way to solve if we are not satisfied with the solution that we got. So we say that f is a function of y alone and g is a function of z alone, and we substitute this fg into the partial differential equation we got, or the elliptic equation we have, and we find that we get an equation that is of this quantity, and this equation can be simplified finally to get f double dash by f equal to minus g double dash by g equal to a constant, and that constant can be a positive quantity, a negative quantity, or zero. And we consider three cases where if it is zero, we get a trivial solution, and if we get positive lambda square, we again get a trivial solution. And we saw this in the last class how it came up. And only when there is a negative uh, constant, we see that we don't get a trivial solution, and we get this lambda n to be 2n plus 1 pi by 2h. Now we are almost towards the end of this derivation. So let me just analyze where we are right now. We found out that lambda n is equal to 2n plus 1 pi by 2h, and we have the solution u particular to be equal to um, 1 second please. Huh. Should be equal to f of y times g of z, and we know that f of y is now represented as a Fourier cosine series and can be written as um, f, since it has
So
infinite number of terms. Sorry.
what is that an on top? I
um
wonder.
yeah, I'll come back to this
Okay.
particular statement over here. For now, I'll just cross it out, because I'll just start from here and then
Oh, we are now at
continue.
lambda. Okay.
Yeah. So we know what lambda n is. Now we have to write this in terms of the Fourier series, and that can be written down in this format, which is given f of y can be written as a naught by 2 plus sigma n is equal to 1 to infinity a n cos lambda n y. Sorry, cos lambda n y. And this a naught is basically we see that this a naught and a n are actually uh, are found from the boundary conditions of this. Let's just I'll just go back here. Yeah, we see that the particular solution has a value of dp by dx h square by 2 mu 1 minus y square by h square at z equal to plus or minus b. Therefore, these two or this a naught and a n are found from the boundary condition of z equal to plus or minus b for up, and at z equal to plus or minus b. I think I don't know what happened. Okay, yeah, sorry about that. For z equal to plus or minus b, we see that up is actually equal to h square by 2 mu dp by dx into 1 minus y square by h square at z equal to plus or minus b. And this equation is what we are I am calling this as, let's say, f of y, and we are using this particular equation to find out the constants a naught and a n, where a naught is given by integral f of y dz by integral oh sorry, that's it, integral f of y dz, and this goes from minus h to h, as this function is only defined in this interval. Beyond that, it's all zeros. And an is given by integral minus h to h f of y into cos lambda n y dy. Oh, this is not dz again,
A
sorry.
naught is a DC value, is it?
dc.
I mean, is it an average value or what do you call that? Mm,
It's an expansion of the half-range Fourier cosine series.
yeah. So does it represent the what in electrical engineering what we call the DC value?
I'm not sure about that. I have
Yeah,
little knowledge regarding that. So, I mean, I think it would make sense because most of these terms do appear in the electrical engineering only. The
yeah, yeah,
Fourier expansion, everything comes in the electrical more than this.
yeah.
So I'm not sure exactly what this is. So, but then we write a naught as f integral f of y dy and a n as f of y cos lambda n y dy divided by cos lambda n y um, this times cos lambda n y dy, and we see that oh, there is a 1 by h over here, and we see that this particular term integral minus h to h cos square lambda n y dy can be written as integral minus h to h. It will be what is cos square theta in
One
terms of,
minus
yeah,
one minus
so
sine.
no, we are 1 plus 2 cos square theta is cos 2 theta.
Right,
So
right.
we write cos square theta as cos
One
um,
minus cos 2 theta by 2.
yeah, cos 2 theta minus 1 by 2, right?
Yeah, sorry, yeah.
Dy, and when we sorry, this is not theta over here, we'll get lambda
Lambda
and
and
y.
y. Yeah.
So when we integrate this, I'm pretty sure we should be able to get the answer as h, and that's where we got this h over here as well. This is basically an inner, so mathematically speaking, this an is basically an inner product of f times cos lambda and y by inner product of cos lambda and y, cos lambda and y. And in a function sense, this inner product refers to the integral between a product of the integral between them, or integral of the product between them, sorry. Yeah, so we'll get a naught and an as so, and therefore we can write this. One second. Yeah, therefore we can write a naught and an, and thereby we can write the particular solution as uh, let me just directly write it as integral sigma n equal to 0 to infinity an cos lambda n y uh, times we'll get um, the other term was e raised to lambda n z plus e raised to minus lambda n z, because we see that the oh, I don't think I've derived it in the last class, did I? I
That's
didn't derive the equation for g. So basically what happens is we'll get g double dash is equal to minus g lambda square, and we'll get g double dash plus g lambda square equal to 0. Um, no, this would be plus lambda square. Therefore, we'll get here as minus, and we'll get g is equal to c1 e raised to lambda nz plus c2 e raised to minus lambda nz, and that is what I have substituted here in this equation.
a homogeneous equation.
Yes, yes. No,
Yeah, yeah,
yeah,
d,
this
yeah,
equation is
yeah,
homogeneous. Yeah.
yeah.
So we once I solve once I put the boundary condition for g, I'll get c1 is equal to c2, and then when I substitute it back, I'll get this this equation over here as an equal to cos lambda and y plus uh, cos lambda and y times e raised to lambda and z plus e raised to minus lambda and z. And based on the boundary condition, I can define a Cn as, let's assume, let me call this as Cn as e raised to lambda b plus e raised to minus lambda b, which can be equated to En. This is again based on the boundary condition. I know I'm skipping a lot of steps in between this and the couple of
Yeah,
steps, but it's pure mathematics and has little to do with
yeah.
whatever we are being derived. So we can write down whatever we have derived in terms of uh, this an as, or this cn and an as uh, the velocity particular solution as sigma n equal to 0 to infinity, uh, again an cos once again cos lambda n y times cos h, again I think this would be cos h lambda n z by cos h lambda n b. So again, I guess I made a mistake over here. This should be an over here and cn over here. And finally, since we have both the equations
Solution.
for u particular and u general, or u parallel plate and u general, we can finally write the actual velocity profile as minus 1 by 2 mu dp by dx into h square into 1 minus y square by h square plus sigma n equal to 0 to infinity. Let me write that down because it will be a big equation. Sigma n equal to 0 to infinity an cos lambda n y cos h lambda n z by cos h lambda n b. This is how we get the equation of the actual velocity profile for let me just box this up, and this is the actual velocity profile for as given in the question, a Newtonian fluid at a steady incompressible, I think the fully developed laminar flow. And we can equate this and find out the solutions of the actual velocity profile, and then check with the CFD techniques in this manner, and find out whether the CFD method is satisfactory or as close to the analytical solution or not.
Yeah,
Therefore,
it
that
will
I
be
think
very
this,
involved.
yeah, this last whatever I've discussed today involves a lot of mathematics which I'm not very keen on discussing right now, mainly because it's as it is, it's way above the topics that is there for CFD. And
Yeah,
if I add on to this some more mathematics, it'll be too much unnecessarily details that I'm going through.
this more goes more into fluid dynamics.
Yeah, and has a lot of engineering mathematics that
Uh,
has uh, taken place.
yeah,
So I guess that's all what I have for today. If you have any doubts, I'll be there for another hour to answer the questions. Uh, anyway, I'll be here anyways for the next 1 hour or something. If you have, I think it's all the what I have from my side is over.
I'm done too.
All right, fine. Thank
Yeah,
you.
thanks. Have a good one.
You too.